Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this presentation I'll be covering CVR FDR, DFDAU and the ELT. So, quite a lot to this one. The cockpit voice recorder and flight data recorder features which are general and common to them both. The emergency locator transmitter, the low frequency underwater locator device, cockpit voice recorder, circuit breakers. We know as crew that there's times we may need to pull those. The flight data recorder, digital flight data acquisition unit, data downloading, aircraft condition monitoring system, and finally a discussion of landing G, or the G recorded on touchdown, and exactly what that means and how that data should be treated. As always, please treat your company training and their manuals as the authoritative source of information. Alright, so starting with the CVR and FDR, say some features general, common to them both. So first off, it's clear the units are very similar, both look very similar. I should say that the FDRs and CVRs aren't the same on all 737s. It depends, sort of when they were purchased, which manufacturer they came from, because they don't all come from the same manufacturer. So they may look, as in the upper images, like cylinders mounted horizontally, or they may look like the bottom image where it's a sort of cylinder stacked vertically. But they're all the same, and they're all made up of basically four components. The chassis, the long bit on the bottom, that's the plinth, just basically to mount it to the aircraft. Also these days contains electronics. There's a PCB in there. The controller is the square unit on one side that houses the electronics that basically put the data into memory. So they process the data that comes into the FDR or CVR and put it safely into memory. The memory itself is housed in the memory module, which is the cylindrical unit, and that's where the tape, or these days the memory chips, are stored. That's crash hardened. That's the strong bit of the whole unit. And then the fourth bit is the underwater locator beacon, also known as a pinger. There are some combi units coming out, CVDRs, but to the best of my knowledge they aren't fitted to the 737. Okay, so let's take a closer look at the heart of it, which is the memory module. This is crash survivable. It's got an inner aluminium cover, an isothermal protection shield, and an outer stainless steel casing, and a further exterior stainless steel dust cover. So it's extremely robust. The manufacturers of these units say that they'll protect data chips from an impact of up to 3,400 G, which is equivalent to an impact velocity of 270 knots, and a deceleration or crushing distance of 45 centimeters. And deep sea pressures down to 20,000 feet, which is just over 6,000 meters. They're also protected from heat of up to 1100 degrees centigrade for an hour by an isothermal insulation, which keeps the inner chamber at a safe temperature. And the photo, by the way, is of the FDR and the 737, where it's located above the rear galley. So there's a hatch there above the rear galley that you can open and just see it and see this. Okay, these photographs were taken from the Ethiopian MAX accident report, and please understand I'm not trying to be sensationalist or gory here, and I'm aware this is a very sensitive subject, but my purpose in showing this is the survivability of that memory module. The The Ethiopian Max hit the ground at over 500 knots, over 33,000 feet per minute, and created a crater of 10 meters deep, which is an image that I'm sure we can all remember seeing in the media and in the subsequent accident report. This upper photo shows that although the majority of that flight data recorder is destroyed, the memory module is pretty much intact. Now the lower photo actually shows the memory chips and connector pad from that memory module. And I will quote directly from the accident report. When opened, the memory board was visually inspected with a Keyence microscope. Apart from the connector pads, the memory board was in good condition. There was no trace of impact. The two memory chips as well as the microprocessor were found in good condition. The downloaded data file provided more than 73 hours of valid data. So it worked. I mean, this was well over the design criteria for Impact G, and it survived with very, very usable data. Now, if the accident is at sea, then when the recorders are recovered from I've specified here salt water. It's particularly salt water, but I believe it also happens, as a matter of course, in fresh water as well. They're immediately immersed in distilled water, as you see in this photograph here. That's what that contains. You may wonder why they would want to expose a recorder to water, but it's actually it's to help, well, two things. One to help clean and diffuse the salt from the recorder, and the second reason is to prevent any oxidization which may occur once the recorders are exposed to air, which may corrupt the data. So the recorders are kept in these boxes of distilled water all the time, from the minute they're fished out of the sea to while they're transported, disassembled, cleaned, all the time, up until the point that the memory boards are extracted. They're then taken out and they're put in a special fan-forced oven or vacuum dryer, desiccator, what have you, for around about 15 hours at 40 degrees centigrade before being read. If memory chips are found to be damaged by either impact or heat, they can be repaired to enable data recovery, and all the main labs in around the world, certainly the British, American, and French labs, and I'm sure other ones as well, have got scientists on hand who can physically repair memory chips. It's amazing work they do. I've seen them firsthand in action, and my utter respect to them. Now, according to the NTSB and the AIB, it's only high intensity or long duration fires that make recorder chips or tape unreadable, and that is fortunately rare. But in the vast majority of cases, the agencies are able to get all the data off these chips. The other component which is common to both the FDR and the CVR is the underwater locator beacon. So it's known as a pinger because that's the sound it makes if you ever hear it. And the way this works is it's got a piezoelectric transducer, which when it makes contact with the water, it activates and transmits this acoustic pulse tone, which we hear of 37.5 kilohertz once a second for a minimum of 90 days. More recent regulations come in and got and has extended this 30-day period to 90 days, and that's in the light of several accidents where recorders have not been found within the 30-day period, and then they've gone quiet. So the present regulation is that they'll now transmit for 90 days. Detection range for these is around 7,000 to 12,000 feet, but bear in mind that there are great areas of the oceans where the depth is in excess of this. And the internal battery, it's got a shelf life of 6 years. Now that's not to say the thing will transmit for 6 years. It won't. It'll only transmit, as we know, for 30 to 90 days. This is a shelf life of the battery until it's activated. So it's an engineering check. I think they do a serviceability check of the battery every 3 years, and then they replace it every 6 years. Okay, so while we're talking about beacons and things, let's take a look at the ELT. Now this is a separate, different ELT to the one on the CVR and the FDR. This is the aircraft's ELT, and most 737s have got an ELT transmitter that is housed in an access panel in the aft passenger cabin ceiling, and as you can see from the photo, it's there above row 30, usually on the left hand side, row 30 on an 800. And there's a decal there which I must admit it was many years before I noticed its existence, but that's the ELT decal up there. And the reason why the decal is there is in case emergency access is required. Now this obviously would be, you know, an off-airport landing, presumably onto land. You wouldn't have a chance to recover this in the water. The ELTs will come onto sea, will activate automatically, but you can rip the ceiling panels out and access it yourself and make sure it's transmitting, or indeed even take it with you if you wish. So that's the behind that panel. So this is above row 30. And you can see the ELT there fixed to the structure of the aircraft. Interestingly, it must be mounted facing the direction of the arrow on it. You'll see in the next photograph that there's a sort of this way forward arrow on it, and that's because it's triggered by longitudinal G. This avoids accidental activation from heavy landings or turbulence. So it must be mounted the right way around. The threshold for automatic activation, it's a deceleration rate of 4.5 feet per second, or 2.3 G. So fairly sharp. Nothing we're likely to encounter in normal operations. The transmitter itself, it's got 2 antenna cable outputs, which you can just about see on that photo. One cable runs the 1215 and 243 megahertz transmissions on a BNC connectoring cable, and the other one runs the 406 megahertz transmissions on a TNC connectoring cable. And the reason why the different cables used is it's to reduce signal loss. Trying to relate this to something you may know, but certainly on the TV signals come into your house. It's different TV cable from a regular old-fashioned antenna, to the satellite dish, and that's because of impedance matching. If you use the wrong impedance cable, then you'll actually get a reflection of the signal, and the signal will be attenuated. So they need to use the best cable, the most matched cable to the signal, to get the maximum signal strength. And the more the signal strength there is, the greater your chances of being found. Is the logic there. This is a close-up of that ELT that's mounted in the ceiling. You can see the forwards arrow on it, and you've got a better view there of the 2 cables coming out. Although it is difficult to see, but they are slightly different widths, and they're different types of cable. But when activated, this, as I've already said, will transmit on 1215 and 243 continuously, except during the 406 MHz transmission, which is every 50 seconds. And it'll continue to transmit until the internal battery pack is exhausted, which they guarantee for 72 hours, or at least 72 hours. The 406 meg transmitter will operate for just 24 hours and then shut down to conserve power, because the higher frequency, it takes more of a drain on the battery. Now, in actual fact, the 406 one is the one that's very likely to be picked up by satellites. and satellites will find it within 24 hours, we are assured. Now, regulations now require that the DLTs transmit on 406 megs. They didn't used to. It just used to be 1215 and 243. But 406 is now mandated, and that's because COSPAS SARSAT, which is the International Satellite Monitoring Agency, they have actually, and this may surprise you or worry you, but they now no longer listen for distress signals on 1215, and they haven't done since 2009 due to the high number of false signals. Which, as you can see in the data there, it's verging on 98% false signals on 1215 versus just 89% on 406. So they cease to monitor it, so that you will only be found by satellite on a 406 transmission. Now the 406 transmitter, it does give a much more accurate position, typically say 2 kilometers, compared to anywhere between 15 and 20 kilometers for the 1215-243 meg transmitters. So 406 is the way forward. We just need to improve battery life to get them able to transmit for longer. The antenna, well, as you can see, the two antenna cables travel the short distance, and that short distance is to reduce the signal attenuation. Again, the longer the cable you've got, the more the signal will attenuate, will reduce. So you want the antenna to be as close as possible to the ELT. So there it is, right there above row 30. To that antenna, which just forward of the vertical stab, if fitted. Now the most 737s certainly have that antenna, therefore have the ELT there. Some don't, and they're conspicuous by the absence of that antenna. Just to compare it to the other antenna, just because I've got this photograph up, it's actually slightly smaller than the VHF comms antenna, the VHF1 and VHF2, which are above and below the fuselage respectively, and that's to match the wavelength of the transmission to the antenna. So as it's using a slightly shorter wavelength, because it's a slightly higher frequency, the antenna needs to be best matched to that. And I forget whether it's a quarter or a half wave dipole, but it's the point is the shorter antennas are used for higher frequencies. And that's what we're seeing here. VHF, which we know to be in the sort of 120, 130 megahertz range, is uses a slightly bigger antenna. The ELT panels, if they're installed by Boeing, they're on the left side of the aft overhead. The bottom two photos are Boeing installed ELT panels. The one at the top's actually off a 300. That's a retrofit. The ELT caption or light on that third-party STC version is just a light. That will illuminate if the LT is being activated and is transmitting. So if that's on, then it shouldn't be. You need to get that switched off as soon as you can. With the switch in the arm position, which is where it's spring-loaded to, the ELT will start transmitting automatically when it reaches the preset longitudinal G-load limit, as we've already seen and discussed. The 2 and a bit G longitudinal G impact will trigger it. You can also manually switch it on if you've got the presence of mind to do that in a situation that requires it. Now the bottom photo actually shows the latest Boeing panel, and this has got an optional reset position. So if the LT light has come on and it shouldn't be on, so there's been something that's triggered it. Then you can move this switch to the reset position, hold it there for 1 to 3 seconds. The book says, well, basically until the ELT light extinguishes, and then you won't be transmitting out on all those 3 frequencies. Okay, this ELT is different. It's a survival ELT, is what it's known as. These are usually stored in the rearmost locker in the cabin, and that's because they're designed to be taken by crew or, well, passengers if they know what to do in the event of an off-airport landing or ditching emergency. These are manually activated, and they're not controlled by the switch in the flight deck. So just because it's an ELT doesn't mean to say that ELT switch in the flight deck will activate them. It won't. These are manually activated and designed to be taken with you if you have to, leave and make your own way from the aircraft. All right, this is a new system, or relatively new system, and it's the low frequency underwater locator device. Now, following Air France 447 accident, which actually took just over a year to find the flight data recorder, and also the disappearance of Malaysian 370. The authorities mandated that from Jan 2019, any large aircraft that's operated more than, and on EASA regs it's 180 nautical miles or ICAO regs 400 nautical miles offshore, be fitted with a low frequency underwater locator device. This is a battery-powered underwater beacon. It's separate from and different to the ULBs that attach to the CVR and FDR, and again, it's also separate from and different to the ELTs that we've just been looking at. So this is an extra, if you like, an additional beacon. There are 2 manufacturers of these that are fitted to the 7.3 anyway. There are probably more for other aircraft. There's the Noviga one, which is about 9 centimeters by 10 centimeters. I'll show you these, and that's usually mounted in the radome on a plate below the glide slope antenna, which is what the photo is here. Now, hands up, it isn't actually in this photo. I haven't got a photo of it mounted in the radome. But when it is, and it is on quite a lot of aircraft now, because this is one of the 2 preferred places to put these, that is where it will be mounted. You can just see at the top of the red oval that I've drawn on the picture, the glide slope antenna, and there's a plate that's sitting on. That is where the LF-ULD would sit, or on another plate just slightly below that, but that's where it would be. The other location is here, up again above the rear galley near the FDR. This model is the other one. This is the Decay 180. And you can put this pretty much wherever you like. The point is, it's absolutely not portable. It's designed to stay with the aircraft. So if the aircraft breaks up and disappears to the bottom of the ocean, then this will stay with it, and you'll be able to find the wreckage. Again, the only maintenance interval with these, it's very similar to the to the pingers on the CVR and FDR. You check the internal battery every couple of years, and you change it every 6 years. And on the decal on these is just the battery replacement date, just to make it easy to know when to replace it if your spare parts tracking system isn't good enough. Both of these, whichever one it is you've got, they will automatically activate on contact with water. That's the trigger. Inside there's an oscillator coupled to the piezo-ceramic transducer ring, so it works just the same as the ones on the CVR and FDR pingers. The resultant mechanical motion transmitted to the metal case of the beacon, which becomes, if you like, the bell, if you like, like banging on a gong or something, and that in turn radiates the acoustic energy or the pings into the surrounding water. This is the big difference. The frequency. These operate at 8.8 kilohertz. Whereas the ones on the FDR and the CVR, they operate at about 28 kilohertz, and this increases the detection range from 3 kilometers up to 22 kilometers with these devices, and that's the big win with these. They are long range because they're low frequency. Specs on these: maximum certified depth 20,000 feet, that's just over 6 kilometers. Detection range of them 12 nautical miles or 22 clicks. They'll emit one 8.8 kilohertz tone pulse every 10 seconds. So again, it's a slower pulse rate than the other ones, and that's to conserve battery life. So the operational life of these is 90 days. So it's to give them every opportunity to be found. Okay, let's take a deeper look at the CVR, the cockpit voice recorder. It's located in a compartment in the right-hand side of the aft cargo hold. You can see in this photo. The actual shape and size of the compartment varies from aircraft to aircraft. Basically, as time's gone on, this compartment has been used for more and more things. You can see in here that there's the APU ECU in there. Well, many operators now also fit the HF transceivers in there, and other stuff is going in there as well. Sometimes the media, the onboard IFE equipment is in there as well. It's just due to a lack of space in the E&E bay. But lack of space in the E&E bay is not the reason the CVR is here. It's there because it's considered to be a more survivable location than the E&E bay. It's kind of stands to reason that the rear of the aircraft is less likely to get significant impact damage than the front of the aircraft. The recording contents of the CVR, and it's probably easier to visualize it on the image I've got there, which is taken from the AIB website. So the CVR will record 30 minutes of audio on 4 channels, and I'll just come on to clarify that now. So what you've got is the captain's headset audio mixed with the captain's hot mic circuit audio. That's labelled up there as CM1. Same for the FO, which is CM2. And the observers, if there's anybody, that's CM3. You've also got a cockpit area microphone, which is the one that you can see on the front of the CVR panel, which is labelled on this as CAM. Now, it will also record 120 minutes, 2 hours of audio on 2 channels, and those 2 channels are combined crew audio and cockpit area mic. So it'll merge CM1, 2, and 3 into one, and CAM, and that's your 120-minute channel there. Recently, ACAR's data link channels, ACAR's data link messages are also recorded as well. These recordings are made onto, all the recordings, made onto the continuous loop tape, or since the early 1990s, solid-state memory chips. As I mentioned, ACAR's messages have been required since 2005 by ICAO standard. Interestingly, even though these are data rather than voice, they're usually recorded onto the CVR. I'm not quite sure why the logic is that they were put onto the CVR, not the FDR, but there we go. That's where they are stored. And the messages that will be stored will be include ADS, CPDLC, DFIS and AOC messages. Basically, any ACARS messages that have been sent or received by the aircraft, the whole lot will be recorded on the CVR. Now, what about recording time? EASA and ICAO have ordered that any commercial aircraft over 27 tons, which is all the 737 family, all large airliners, built after Jan 2021 must be equipped with CVRs that can record 25 hours of data. So this brings them into line with FDRs. Now, just because it's an ICAO rule doesn't necessarily mean to say it's a national rule. Now, in the Eurozone, EASA have followed suit. The NTSB, well, the FAA, I should say, who make the rules, are lagging behind a little bit, and the NTSB has called for the FAA to follow suit by 2024. I would imagine operators can see this coming and will choose to re-equip their aircraft early voluntarily before this deadline's met. And the reason for this is to enable data to be available for less severe events, and this is where events such as where electrical power is maintained, so runway excursions, engine failures, tail strikes, or any survivable flight control malfunctions, because you could have well, say an engine failure or what have you, or a flight control issue in flight, and you could be a long way from where you need to land, and by the time you land, God understand, pull the circuit breakers, the data of interest could have been overwritten. So that's why the ruling is to extend this up to 25 hours. Quick look at the panels. This is all the way through from the very first 737-100 at the top down to the sorry, no, because they weren't on the original. This is from my apologies. This is from the classics through the NG to the Max. It's changed very little over the years. As I say, there was no panel on the originals. My mistake. The erase button, by the way, will only work when you're on the ground with the parking brake set, so no use pushing that in flight. The test button will generate a test tone that can be observed as a deflection into the green on the sound level meter if you've got one of those on one of the early panels. If you haven't got a sound level meter on yours, then you can just plug your headset into the headphone jack, and you will hear the tone through that. The times of operation, not as straightforward as you might think, really. The CVR is powered from first engine start. I think it's when the N2 gets above about 55% from memory, until 5 minutes after the last engine is shut down. There's a new bit of kit called RIPS, which I'll mention in a moment, which actually extends that out to 10 minutes. Some aircraft have got this panel that you see here, which is the auto on switch. It's on the top right of the overhead panel, just above the air conditioning panel, and this enables crew to manually switch on the CVR before engine start. And some airlines, certainly the airline I was with, mandated the crew do this as part of the cockpit preparation, so that all the checks and briefings and what have you can be recorded. That switch, it's solenoid held, and that will click back to the auto position during the first engine start. I say around about 55% N2 from memory. Okay, quick word about the use of recordings, because I know this is something that we as crew are a little bit twitchy about. I mean, years ago I used to fly with a captain who religiously would erase the CVR after every duty, because he was paranoid that the company were downloading the CVRs to listen to what he had to say. I'm sure they weren't, but anywho, let me say what ICAO says about this. CVR recordings, obtaining accident investigation, they're treated much more securely than FDR data, and it stands to reason that this is because of the highly sensitive nature of some verbal communications in the cockpit, because of course before the accidents or the incidents happened, I mean you just talking to your mates on the flight deck, a normal day out, so you kind of unguarded, if you will, and things can be said that you wouldn't want people to hear. ICAO are aware of this, and they are sensitive to it, and it's actually written into Annex 13, and I've put a couple of extracts there on the right hand side for you to read. So ICAO Annex 13, which is the best practice that most countries are signed up to, requires that the investigation team keep CVR audio recording confidential and out of the public domain. Furthermore, the content and timings and timing of release of any written transcripts are also strictly regulated, so that only pertinent portions of the CVR are released in the final report. And hopefully that gives us some comfort that the data isn't being misused or will find its way out onto the internet. Now, I'm sure we've all heard CVR extracts on the internet. I mean, I've heard a couple, and they're absolutely chilling. But it's that should not be happening, and I believe it's happening less and less as these regulations are filtering through to all the countries they need to. Okay, let's just sort of dodge sideways a bit to talk about circuit breakers. Obviously, circuit breakers to do with the FDR and the CVR. Now, in the event of a significant incident, crews are advised to pull both the CVR and the FDR circuit breakers after stopping to avoid data erasure as the tape records over itself. We all know that. What I think we perhaps don't know, or are less sure about, is exactly which circuit breakers do we need to pull, because it isn't actually as simple as it once was. This photo is a photo of the circuit breakers on a 737 Classic. They're actually in the same location on the NG. They're over the captain's left shoulder on the P18 2 panel. Now, on this you can see voice recorder. It's dead easy. There's just one circuit breaker, so that's a no-brainer. You pull that. For the flight recorder, you probably see two circuit breakers, the AC and the DC. I'll tell you, and I'll explain in a moment, that the position sensor is also to do with the flight recorder. So there's potentially three circuit breakers there. So which ones do you pull? Well, I'll explain. I should say, that it's illegal to stop recorders in flight. So this should only be done by crew after a significant incident. Okay, so let's talk about the CVR CVs. Now, this photo is from the panel of an NG, and you can see that there are actually two circuit breakers rather than one as there were on the Classics. Voice recorder relay and voice recorder. The relay is just a time delay circuit that allows the CVR to continue to operate for 5 minutes after the engine's been shut down. That's all that is. The one labelled voice recorder is the one that you need to pull. Now, what I say is, if you don't remember this, and really you could be very well forgiven for not remembering this in the heat of the moment, if in doubt, just pull them both. You're going to do no harm at all by pulling both circuit breakers. But as this is a technical presentation, if you like, I'm telling you that the only one you need to pull is the voice recorder one. But as I say, heat at the moment, pull them all. It really doesn't matter. On this photograph, you notice that this particular one has got a red collar around it. That's an optional feature that this particular airline, they put a little stash of red collars there for crew to use after they've had to pull the circuit breaker, so it's identified. I mentioned RIPS briefly earlier on, so that this is the RIPS CD, CB. So you can see that we're now up to 3 circuit breakers for the voice recorder. Again, the only one you need to pull is the one labelled voice recorder, but pull all 3 if you want. RIPS is recorder independent power supply, and this is a new regulation that's come in to extend the recordings to 10 minutes after engine shutdown, or in fact after loss of electrics. So what it's got is a dedicated battery pack, which is actually powered from the 28 volt DC bus too. So the operational difference is that with RIPS, if you have a loss of electrical power in flight, the CVR will continue to record for 10 minutes after that using the RIPS battery pack, so that the investigation authorities have got more data to go on. Because what's been found is in a number of instances, and I think the Swissair 111 was one of those, where CVR and I think FDR data was lost early, because the onboard fire caused a loss of a total loss of electrics before the final moments of the aircraft. So the aircraft kept flying for a while after all electrics had been lost, and that data was not captured. So that hampered the investigation process. So that's what RIPS is about. I guess the other thing that we should know is in ops normal procedures, it'll continue to record for 10 minutes after a normal engine shutdown instead of the usual 5 minutes. The flight data recorder, as I've already mentioned, there are 3, as you can see on the NG. They've extended the flight data recorder labelling bracket to include all 3 now. The AC circuit breaker is the one that you need to pull. That one depowers both the flight data recorder and the digital flight data acquisition unit. So if you only want to pull one, that's the one to pull, the one in the middle, the AC one. If you just pull the DC one, then that will depower the FDR control interface circuits. It'll certainly remove power from the control interface, and I believe that from that point the FDR won't record anymore, but it won't remove power from the digital flight data acquisition unit, so potentially ACMS data could still be being recorded. The position sensor circuit breaker only cuts off power to position sensors, and they are things like control surface position sensors and control column position sensors, and I'll explain later in this presentation and show you examples of those. You don't need to pull that, but again, I keep coming back to this point. If you're in any doubt, and you're likely to be after a significant event, just pull the whole lot. Don't worry about it. Okay, so let's take a close look at the flight data recorder now. As I've already mentioned, this is located in the ceiling space above the rear galley. It's not in the E&E bay because the rear of the aircraft is considered to be a more survivable location than the front. This we know. There have been several different models of the FDR, and current models can collect 25 hours of data from hundreds, absolutely hundreds of parameters. The panels, the old panels looked like this, and by this I mean that these are panels from the 737-200, and I think the bottom one was actually from an early classic I flew. But what you do is you put the flight number and the date into the panel manually during your pre-flight checks. In the after start checks, you press the repeat button, hold that for 5 seconds, and that transcribes that trip and date number onto the metal tape, and you get a little amber light illuminating while you're pressing that button. If you have an event in flight that you think needs flagging up, then push and hold the event button for more than 5 seconds to mark the tape. The gauge whilst it looks very similar to the gauge on the CVR, it's actually different. This is hours remaining of the tape, so it's not a level meter. It's hours remaining of the tape. Full scale deflection, you've got more than 200 hours. The new panel just looks like that. It's simply got a test position, which should make the off-light extinguish, and the normal position. And that's because the new FDRs don't have foil or magnetic tape, so you don't need the functions of the upper panel. FDRs start recording as soon as the first engine is starts, and they continue to record for as long as electrical power is available. If electrical power is lost or you get a failure of the FDR, the off-light will illuminate. So looking at the media for the first FDRs, this is a bit I can show you here, and this is again from the originals, the 737-1 and 200s, and you probably find it surprising to see how little information they recorded. There were just 7 metal scribes, and they etched the data into there were either 150 foot or 200 foot long of roll of 5-inch wide stainless steel and nickel foil tape. And stainless steel nickel foil was chosen because it's got high resistance to mechanical damage, heat and corrosion. So in other words, it was survivable. It had good survivability. This foil moved along the drums at 6 inches an hour, so you can record for 300 hours or 400 on the 200 foot tapes before the spool needed replacing, or you could turn it over and get another 300 or 400 hours off the back of it. But if you look at those parameters, all you've got are altitude, airspeed, heading, vertical acceleration, and the time of any RT transmissions. That's it. It's really basic. How on earth accident investigations could do a meaningful job with that little data? I don't know, but that's what they had. Fortunately, things have moved on. This was the next stage, and the foil ones were replaced in 1989 by so-called digital FDRs, and these could record 25 hours of data onto a 1/4 inch 450 foot long magnetic tape. So we're onto magnetic tape here. The versions of these on the 737, they could record up to 18 parameter groups for up to 25 hours, and the list is down there in blue of what they could record. So much more comprehensive than the old tinfoil things, but certainly a lot less comprehensive than the modern recorders. So the modern ones started off looking like this, and this is one extracted from an unfortunate 737-200. But you can see there's no tape. It's all chips. So from 1991, these were. It was required that all new aircraft were delivered with these solid-state FDRs. They can also record a minimum of 25 hours of data, and they can record potentially hundreds of parameters onto several memory chips. There was also a requirement for a minimum of 35 parameter groups to be recorded, and that led to the development of the Digital Flight Data Acquisition Unit to collect and process both all the legally required data and any additional data that might have been required by the operator. So let's have a look at it, the Digital Flight Data Acquisition Unit, or I call it the DFDAU, but that's probably incorrect. So those are three different ones used on various generations of 737. So they didn't have this on the originals because so few parameters were required. On the originals, the data was just fed directly into the FDR, and that data was simply altitude and airspeed data from the air data computer, heading from the FO's RDMI and acceleration from the accelerometer and wheel well. That was it. That was all you got. But with the DFDRs, you could record many more parameters. So these units here, these digital flight data acquisition units, they gathered the information to be sent to the FDR. And now these can not only collect the mandatory data required for the FDR, but also the non-mandatory data, and that's known as ACMS, or Aircraft Condition Monitoring System, for airline use. And I'll talk much more about that as we go on. So let's have a look at what data it actually collects. The data sources. There's three types. The first is discrete, and this is just straight binary on or off data. So switches, relays, valves, anything where it might be useful to know whether something was on or off. That's discrete data. And there's a long list of discrete data collected there. The next sort of classification, if you like, is analog. And these are things with a numerical range, so it's not just on or off. It's a scale. So the accelerometer, a scale from, I don't know, -4 to +6, whatever it might be, is on there. Spoiler sensor position, so any primary flight control positions or control column positions, where there's a range of values. That's analog data. And the final type is digital data, and this is more detailed, sort of non-numerical data. So this could be things like modes, error codes, that sort of stuff. I mean, there's a whole load of data. I mean, a world of data that is recorded. I mean, you'd really be surprised. So let's have a look at this as an example. So just taking one of those parameters from the digital sources, so the flight control computers, and you can see that there are, I mean, I've got two columns of data parameters which are taken from the FCCs alone. So it's stuff like all the mode control panel selections, all the autopilot modes, any warnings that may appear, any push button selections. Huge amount of data, and that's just from one of these digital sources. So you're hopefully starting to get an idea for the vast number of parameters that are collected. Analog data is different. So I mentioned earlier that the control wheel and control column position sensors. So these are where they are. You might just remember this photo from I used it in an earlier presentation for, I don't know, flight controls, I think. So what we're looking at here is through the hatch from the forward electronic bay. So it's not the E&E bay, but the forward equipment bay. And you're looking in and sort of up underneath the control columns. You can see the counterweights on underneath the two control columns there. So again, if you find the sort of circles below the control columns, you'll see a kind of white curly wire coming off them, and they're going back to control wheel position sensors. And up above is the control column position sensors. What one's actually covered by that white blanking mask, but that's where they are. Now these use synchros to generate electrical signals, which basically correspond to the amount of movement of the control wheel or the column. There are similar sensors recording the positions of the rudder pedals, the speed brake lever, and the flight control surfaces as well. The accelerometer you'll find in the wheel well. Vertical G was one of the few original parameters, one of the original 4 or 5 parameters that had to be recorded. So the 737's always had an accelerometer in it, and it's always been in this location. The only difference over the years is that the present one is 3-axis, so it'll measure vertical, lateral, and longitudinal acceleration. Excitation from the 28-volt DC supplied by the flight data acquisition unit. It's a self-contained sealed unit mounted on a shelf on the forward wall of the wheel well, actually just behind the B system hydraulic reservoir, which you can see just left of picture. And it's there because that is the one position on the aircraft which is considered to be closest to the centre of gravity, and that's so that the accelerations are not influenced by pitch, roll, or yaw. So that's supposed to be the truest indication of acceleration at that point. All right, data downloading. Let's have a little look at how that's done. This is the first digital flight data acquisition unit that was used on classics, and some early NGs had this same model. You can see the manufacturing date there. It's 1999 on that particular one, to give you an idea. Now, on these early units, data had to be manually collected from the aircraft. There's a hatch there you can see I've labelled on the front of the unit. If you open that, inside there's a PCMCIA card that can hold 500 meg of data, and engineers would have to periodically go into the E&E bay and switch out a full card for an empty one, and take the full one back to the airline for data processing. And life went on like that for a decade or so. The other way of doing it was actually with the data loader in the flight deck. This is usually used for updating system software, but you can actually download ACMS data onto a floppy disk or using a portable data unit. And you've got an FDR test receptacle there as well, just for remotely testing the FDR. Now, later DFDUs look like this, and this is still the most commonly used one. This is a Teledyne. This is the one. Assembly date of that particular unit, just reading it off the picture there, is 2009. Most of the NGs have got this. And what this has got is, you can see down the right hand side there's a drive there for a hatch for an optical drive, so a CD or DVD. And these have got obviously greater storage capacity than the PCMCIA cards, which is reflective of the greater number of parameters that can be gathered by these units. Now, instead of having to switch out a PCMCIA card or a CD, the previous flight data acquisition unit is almost always used with a quick access recorder, and these are what they look like. And these are also in the E&E bay, usually next to the DFDAU. Now you can still use a PCMCIA card if you wish, but you will notice that these have got Wi-Fi antenna on them, or wireless antennae. And what happens with these is that when the aircraft has landed, the aircraft engine shut down and door 1 left is opened, these automatically transmit all that data back to the operator. So there's no need to use PCMCIA cards or CDs or anything like that anymore. All the data travels via the wireless link. On the Macs, the digital flight data unit looks like this. I think it's also in use on some late model NGs as well, but I'm not quite sure. It's certainly in use pretty much exclusively on the Macs. Behind the hatch on that, there are a couple of serial ports, a couple of RJ25s and an RJ45, and these use CFast cards to download data if Wi-Fi is not available. CFast it's pretty much the same as PCMCIA, only the storage capacity is much higher. You see just on that illustration, that's a 16 gig card instead of the half a gig card on the PCMCIA. These do things slightly differently on the Macs. The QAR is no longer wireless per se. It uses the onboard network file server from the ONS, so that the data can be transmitted wirelessly via the aircraft's wireless LAN unit, or you can download it onto a portable maintenance device from the network file server. So again, it's just taking things that step further. Right, ACMS, Aircraft Condition Monitoring System. Let's have a closer look at this. So data distribution, because all this data is being collected. Let's see where it goes and how it's used. So your digital, analog, and discrete data sources are all collected by the digital flight data acquisition unit. That converts those parameters, the ones that are required by regulation, into what's known as ARINC 717 format and squirts those down to the FDR. Data from the FDR and CVR is never normally read or extracted or read unless there is a serious incident or accident. So that's in there, that's safe, that's sealed, and that's overwritten every 2 or 25 hours depending what the data is. The ACMS parameters required by the airline are fired off via the QAR. Now, so I used to work in an airline safety department, so I'm quite familiar with the many uses of the data. I mean, we as aircrew tend to think, oh God, it's just the airline, watching us, Big Brother style. Obviously, they do monitor flights for exceedances and behaviour and the like, but the vast majority is used by engineering for engine health and exceedance data. And I've spoken to the engineers in a major airline who pore over this data real time, and they look at trends of data, and they can predict failures in engine components before they happen, and they will do that, and they have. They've pulled aircraft off the line. They've turned aircraft around in flight. They've messaged crew and said, look, turn around, come back. We got an engineering issue, and replace components before they've had an engine failure. That's how advanced this is. It's not necessarily all done in-house by the airline. Sometimes it's done by GE out in Cincinnati. And the airline engineers might get a phone call from Cincinnati saying, look, you've got a problem on one of your engines. But this is really where it is, and I know we as pilots can be paranoid at times, but really it's not all about us. There's much more to it. So anyway, I say engineering use the vast majority of this data. Other departments that use it, well certainly where I was involved, the legal department often came to us for data, for release of data, and you might wonder why, but sometimes you get claims in by passengers of, say, whiplash or what have you, for a claimed or alleged heavy landing. So the legal department might come to the flight data department and say, look, can you give me the touchdown G for such and such a flight, and they will then go and handle it. Or departure time data, and that's for things like EU 261 claims for late flights. As you're aware, in Europe, if a flight's more than 3 hours late, then passengers have got a right to claim a certain amount of compensation. So the legal department will look for what time the doors were closed, what time the aircraft pushed back from this data. Ground ops departments may want door opening and closing times so they can watch the performance of the ground handling agents, to see if there was a delay between the last hatch closing and pushback, or how long between arriving on chocks and the parking brake being applied and the first door opening, that kind of thing. But as we know as pilots, the safety departments use a lot of this flight data for flight monitoring and for debriefing crews on events that have happened. And hopefully your airline, like mine, uses it in a sympathetic way as an instructional and teaching tool, rather than as a stick to beat you over the head with. The ACMS panel, if fitted, and I haven't seen very many of these fitted, but if you are, it's dead simple. It's got an event button and a print button, and the event button's just the same as the old tape FDR panels. You press that if you think something significant's happened that a department may need to know about, and if you want to see what it was, you press the print button and out it comes from the printer. That's that. Now, if you want a more detailed look at parameters, then this is a way to do it. So there are a number of different systems on the two that I know of on the 737, and they've got different ways in and routes through, different sort of navigation trails through the menu. So I'll show you them both. This is the first one. I'll show you, and if you on your CDU select menu, then ACMS alpha display, or alpha menu display, you'll get the menu there, which is the alpha call up menu, and in that you can type, if you know what code to type, and it will put it in the field, and it will populate it with the data from that. Now, some example codes are ACID, aircraft ID, EPUH for the APU operating hours, engine cycles, engine hours, pitch trim position, minimum vertical G during flight, maximum vertical G during flight, and the one that pilots are most interested in, which is VGTD, which is the vertical G at touchdown. So if you go through those steps, you can pop in your VGTD if that's the one you wanted to see what your touchdown G was recorded as. I will come on to discuss this particular parameter in detail in a moment, but this is how you see it anyway, the raw data. Now, there are hundreds of these codes available. I mean, literally hundreds. If you want to see them, then just select Alpha List on that third screen there, and you'll get pages and pages of them. All right, so that's method one. Method two, with a different system, you go in this way again. It's ACMS, DMU menu, parameter display, menu call up, and then choose landing analysis from the parameters menu, and there are 4 pages of these. So you want to scroll through to page 3 for landing analysis, and on landing analysis you'll see a field called VRTMX, which is the touchdown G there. I say it's very confusing because not only have they got different routes through, that the label, the same label has got a different name. Why there are 2 systems, I don't know, but you would have thought they would have harmonised it. But anyway, that's what you've got. Just following on from the system 2, if you want to see all of the possible parameters, then go alpha call up and select help, and you can scroll through pages and pages and pages of the available alpha list there. Knowing what they mean is a different kettle of fish. I mean, you can guess most of them, but anyway, that's where they all are. This is just, I say, for transparency, so you know what's there. Right, I promised I'd talk about landing G, and I will, and here it is. This is the last thing on this video, but it is quite important because I know that this is the parameter which is of probably of most interest to pilots. Whether it's professional pride that they of course we always strive to do smooth landings, or whether it's just fear of the company coming down on them for doing a heavy landing. Whatever it is, it's certainly one that we're interested in. But let me take you through what this actually means and the limitations of it. So first of all, I have to say that this parameter should be used with caution, so much so that even Boeing believe that pilot judgment and reports describing the landing rather than ACMS are the best source of information for ascertaining if a hard landing has occurred. And this is partially down to sampling rate. Now, what you need to know is that the sampling rate, i.e. the number of times that a reading is taken, can be either 1, 8 or 16 readings per second on the 737, depending on the hardware and software on the particular aircraft. So what does that mean? Well, this is what it means. If the sampling rate is low, it might not capture the peak G of landing, and it'll therefore underestimate the severity. Now, what the graphic I've got here is an FDR trace from a heavy landing that occurred to a 737-800 in the Azores, I think it was, a few years ago. Now, what I've done is I've superimposed on that 5 red lines with which are occurring at once every second, and you can see that depending on the time at which those 1 seconds fell, I've got readings there of 0.9 G, 1.2 G, 0.6 G, 1.9 and 1.1. The actual peak G was believed to be 3.52, and this hasn't shown it. In actual fact, what it's shown is not even the peak G on the bounce, but it's shown that because this aircraft bounced, and which is why you've got the negative G part there in the darker colour, and then unfortunately it landed on its nose wheel for that second impact just before 4 seconds on this scale. So you see, depending when those samples were taken, you might not have got the peak G. That's at 1 sample per second. If you have a high sample rate, and you will get a better chance of capturing the peak G of landing. Now, notice I say better chance. It doesn't absolutely mean you will get the peak G. Now, I've shown on here only because 8 samples per second, and that's, I say, only because it would be too busy to show you 16 samples per second on this graphic. And to be honest, I was going cross-eyed doing this, but you can see that even at 8 samples per second on this way of doing it, starting at the 2 second marker, we've looked to have captured a 3.5 G peak. And you can imagine that at 16 samples per second you would have an even better granularity and a better estimate of what the true G was. So that's the effect of sampling rate. Now, sampling rate isn't, unfortunately, the whole picture either. There's another factor. Okay, you recall I've showed you that G was measured in the wheel well near the centre of gravity. Well, that only gives you the G there at the centre of gravity. Boeing in an attempt to try and calibrate G with heavy landing damage, because what they were finding was that G was not. They were having lots of heavy landing damage. Well, I say lots. There were plenty of heavy landing incidents being discovered where the recorded G was low. They knew the real G must have been higher. So in I say around about 2000, they did an experiment whereby they put accelerometers throughout the aircraft. And also sampling at a fairly high rate, and that revealed significant variations in both the time and magnitude of G due to factors such as aircraft weight, CFG position, Motion, and by motion this can be anything from sink rate, forward and side velocity, roll, pitch, yaw angles, and rates of yaw, pitch and roll. All of those were affecting it. Furthermore, external forces such as gust loads, ground effect and runway contact loads, and structural dynamics, so vibrations and harmonics, were all feeding into the G picture. So the graphic on the right, which I concede is quite difficult to follow, but that was the one they issued, shows that the tests were done on all 737 models that were current at the time. So unfortunately the 900 was not on the list. And what they did was they correlated this data, sampled at 8 samples per second, with the maximum design sink rate, which is 10 feet per second. Because again, I should say that the Boeing don't have a hard landing G threshold. What they have is a hard landing sink rate, and the threshold for that is 10 feet per second. But anyway, they were trying to correlate what the accelerometer records in the wheel well with the sink rate, so that they could come up with a meaningful hard landing inspection threshold of recorded G at the CG. And the inspection threshold they got, it's actually slightly lower than the lowest data point to minimise the number of nuisance inspections without exceeding the design sink rates, which might seem counterintuitive, but what they were finding was that operators were doing more heavy landing checks than were required, because basically the crew weren't that calibrated, that they were overestimating how heavy the landing was. So good on the crew, but obviously it takes an aircraft out of service for longer than is necessary. Anyway, so what they came up with is this graph here, or this envelope, and whilst we know that there is no single G figure that defines a hard landing, engineers have now, since about 2000, this came into the maintenance manuals for them, they will now perform a hard landing inspection only if the G exceeds the figures in the graph shown here, or of course always if you report a hard landing. Note that G threshold is lower for a lower sampling rate aircraft, because they have to be on the safe side. I think that's going back to what I showed you about the effect of the low sampling rate. And also if the landing was above the max landing weight plus half a ton. This graph is actually valid for all 737s except for the max 10. So all NGs and all Maxes except for the 10, and the reason why the 10 isn't included in this is because it's a longer body, so there can be more effect at the extremities, in particular the nose wheel. Nose wheel landing inspections are something which can create quite a problem for engineers. So the thresholds are lower on the max 10. So that graph, it's actually only valid for aircraft which sample at 8 degrees per second or more, and that the angle of bank got to be less than 6 degrees, and that the landing wasn't bounced, because with bounce landing there is a real risk of a nose wheel landing. Anyway, the bottom line is that if you feel a landing may have been hard, please tell the engineers, as the ACMS data may not have detected it. So that's the takeaway message there. That is it. As always, if you've enjoyed the video, please give it a like, subscribe, consider getting a copy of the book if you haven't done so already. All this information is in there, or at least will be in an updated version as I make the videos. Thank you very much for watching.